Okay, let's continue our morning session. And the next speaker is Xiaomeng Xu from Peking University about Stokes phenomenon and integrability.
Okay,
Please.
thanks for the introduction. It's my great pleasure to be here and to report my recent works on Stokes phenomenon. And like like the title, so there is a soft part that is to construct certain quantum algebras like quantum groups, Yangians, or elliptic quantum groups, and so on, via the Stokes phenomenon. Roughly speaking, to construct solutions of Yang-Baxter equations via the so-called Stokes phenomenon. So I call it soft because there is no analysis inside. But somehow there is a hard part, which is after you build a relation between Yang-Baxter relations and Stokes, and then try to use the representation theory of quantum algebras to solve some open analysis problems. That is to solve certain so-called isomonodromy deformation, some nonlinear Hamiltonian system deformation equation. So this is a plan of my talk, but first I don't know if I mean if, I don't know if Stokes phenomena is known to the audience. Could I give a brief or general introduction to it? Okay, I should then. Okay, yeah, because maybe it's not so well known. So maybe it's well known that given a meromorphic ODE on the complex plane with regular singularity, any formal solution is automatically holomorphic. But somehow it's less well known that given a meromorphic ODE with irregular singularity, then given a formal solution near the irregular singularity, I mean it's not it's in general it's divergent. So the Stokes phenomenon somehow describes this such a phenomenon. So let's first give an introduction to the so-called Stokes phenomenon. Stokes phenomenon. So roughly speaking, it says that a complex function can have different asymptotics. A complex function fz can have different asymptotics as z go to the critical point from different directions, sectoral directions. So here I give you two examples, like exponential 1 over z. So it has different asymptotics when you approach to the origin from left, either from left or right, and the asymptotics jumps along the real axis. And another example is so, for example, I can take humorous function. So with the argument z and ab are two complex numbers, and we know that this function has a essential singularity at z equal to infinity, or let's say 0. And as z approach to 0, it has the following asymptotic expansion. I don't remember it by heart. Maybe it's not quite right, but just give you a rough idea how it works. So as z go to 0, for example, then you can see that if z go to 0 from the left, this function is exponential growth. Otherwise, it's polynomial growth. Therefore, it has different asymptotics behavior in different sectoral regions. And the Stokes phenomenon is actually a very common phenomenon to almost all the special functions. So like in these two examples, so we have some special functions and it can have different asymptotics. And one can introduce some data to measure the difference of the asymptotic expansion. On the other side, we know that the Yang-Baxter relation is sort of Bride relation. So in the first part of my talk, I gonna make this, so, so this jump on the left looks like the braiding on the right. I will make it precise. So in particular, I will take some differential equation and study the Stokes phenomenon of its solutions in an irregular singularity, and then show you that this jump is exactly a solution of Yang-Bak's. This is more or less the first part. Okay. And then I gonna, well, like in these two examples, the special functions are solutions of ODE. So more generally, I can take a meromorphic ODE with an irregular singularity. So for simplicity, let's take the simplest one with a second order. That is, I consider the following differential equation on the complex plane. So with a second order pole. So here I assume U is a diagonal constant matrix with distinct eigenvalues, U1 to UN, and I assume A is an arbitrary by matrix. Then we recognize that any fundamental solution of this system, let's say Fz, is a fundamental solution. So in general, any fundamental solution will have origin as an essential pole. Therefore, any solution will have such phenomenon. Now let's give you more details. I'll try to tell you what's the Stokes phenomenon of this differential equation. So first, we can find the formal power series, matrix valued power series solution. And the ansatz takes the following form. So this is identity, n by n identity matrix has some unknowns. So I take a formal power series around the irregular singularity, and then times some singular part. This bracket A takes the diagonal part of matrix A. So this is a formal power series solution, and this is viewed as the initial data. This is the initial value. And then if we plug in this formal solution into our system and compare the power series on the left and the right, we will immediately recognize that these unknowns HK satisfy the following relation. The bracket of these two matrices, and by matrix is given by A times HK minus HK times the diagonal part of A, and then plus K times of HK minus. So if U1 to UN are distinct, this recursion relation uniquely determines all the HKs. But somehow, just from this expression, we have K on the right. Therefore, a simple estimate tells us that if we take any matrix norm, you see that the norm of HK is more or less K factorial. Therefore, this solution is only formal. The convergent radius is the radius of convergence is simply in general 0. So it's a common phenomenon for meromorphic ODE with higher order poles. Okay, but somehow, so we only get a formal solution. But somehow we can use a Borel summation to resum this formal sum, and then to get the actual solution. Let me give you a quick review on Borel summation step. Yeah, now I'm telling you the Stokes phenomenon for the solutions of this equation at the second order pole, z equal to 0. Now let's take we only get a formal solution, but still we can do the Borel summation. I denote this formal power series part by HK hat. H0 is the identity matrix. Another thing is that we divide each term by K factorial and then multiply K factorial. And now we replace K factorial by gamma function, which has an integral expression, I guess. maybe minus k or plus k. I don't quite remember, but we replace this by this integral expression, then plus. Okay, great. Okay, good point. Yeah, and then we formulate. So we have two summations, one with respect to k, and one with respect to t. We formulate switch the order, then we get integration like this, hk. So we move times t power of tz power of k, and then times the exponential minus t, I guess. Right. So if I introduce a new operator, just for simplicity, then what we get is this function. I guess. Yeah. Okay. So we get a. So we replace formula. So here, so this is where the resummation happens. So formula we rewrite this form power series as an integral expression, and this is a function, now a matrix value function, at by g of t. Another thing is that since we have hk is like k factorial, therefore this function of t is holomorphic near the neighborhood of the t-plane of the baroplane. Stokes matrix? Yeah, I haven't, not yet. Yeah, yeah. Now I'm telling you how to get actual solutions in different sector regions around zero. And then the different solutions, the transition between these different solutions are the so-called Stokes matrices. So we are almost there. Yeah, exactly. So basically here I use the Borel-Laplace transform, but I don't want to introduce new notations. Yeah. Okay. Now the thing is that as long as we can take the analytic continuation of this guy to infinity, and in the meanwhile, if this is controlled by exponential growth, then this is a holomorphic function for all the z's such that the real part of T over z is bigger than 0. So this is out. And in a summary, so this is the idea of Borel resummation. So in a summary, we can introduce a so-called Borel-Laplace transform of h hat along a direction d. So here is so here this d is a direction. I take any direction on the t plane. So basically, I rewrite this integral expression, but instead I take the integration path from 0 to infinity along the direction d. This is the only difference. G of t, the matrix G of t and times. Now, as I said, if I can take the analytic continuation of G of t from 0 to infinity along direction d, and in the meanwhile, if this is exponential growth when go to infinity, then this is indeed a holomorphic matrix value function for all the z's such that the real part of T over z is, is positive. Yeah. So in a summary, now I can tell you for which direction d this is indeed the case, and I call it a fact, maybe due to at least known to Birkhoff or maybe earlier, that actually for all the directions, but the finite many ones, the so-called Stokes race, times ui minus uj. So here, recall that u1 to un are the diagonal part of u. So I take the difference of ui to uj, project it to the complex plane. Then I will get finitely many points. So these are the reals from 0 to through this points. So I have finite many of them. These are the so-called Stokes rays, or by physics, anti-Stokes rays. And actually for all the direction, but the finite many ones, the Borel Laplace transform of H hat is holomorphic. Matrix valued function defined on the sector region E. So here this is a sector. So if I take any direction D, so this is a sector with a bisector direction D and with the opening pi. So if I take this direction D, do the resummation, and then this is a sector, basically. Okay. And another simple fact is that, when we do this resummation, we only switch the orders of taking sum. Therefore, it's automatically compatible with taking differential of z. That is, whatever differential equation of this formal sum, formal H hat satisfy, so does this Borel Laplace transform. Therefore, I can define this holomorphic matrix valued function as the Borel Laplace transform of this formal part times, because that we have this irregular part. Then this is automatically a fundamental solution of our system. Fundamental solution. But only defined on a sectoral region. And in the meanwhile, this fundamental solution has a prescribed asymptotics. Recall that when we talk about, recall that any the set of fundamental solutions of ODE is a vector space. When we take initial value, we take a basis of this vector space. It's important to remember the basis. So to get this solution, we take a initial data. That is, it's a fundamental solution with a prescribed asymptotics. That is FD Z times is asymptotic to 1 identity matrix within sector. Okay, so basically, given initial data, the identity matrix, we first get a formal solution, and then we use a Laplace transform to get actual solutions, but only defined in certain sectoral regions. Another thing is that this solution depends on the choice of D. Right? How does it depend on choice of D? Let's do a small exercise. So for example, if we have two different directions, like D and D prime, if D and D prime are in the same sector, so if there is no Stokes ray in the between of D and D prime, then FD and FD prime coincide with each other. So another thing is that what happens if we vary D? So as I said, if D and D prime, so for example, if there is no Stokes ray bounded by the two edges in between of direction D and D prime, then the fundamental solution we get coincides in their common domain. Yeah. Well, let's prove it. So basically, FD and FD prime. So how to compute them? So one is The one is the integration from D, and one is integration along D prime. Okay, so these two guys equal to each other. Why is it? So we can always close this D and D prime to get a triangular. Then the integrand is holomorphic inside, because G of t can because G of t, the function, this function G of t can only have poles. Recall that a priori is defined near t equals 0, but then it can be analytic continuate to infinity along all the directions, but the finite ones. G of t can have critical points, poles along this Stokes race, but it's holomorphic inside. Therefore, if we take this triangular, the integrand is holomorphic by the Cauchy theorem. So these two guys only differ by the integration along this edge. But somehow along this edge, the integrand is exponential decay, which is 0. Therefore, they equal to each other. But somehow, if there is some Stokes race in between of E and D prime, so we can use the same argument. For example, we take D prime prime. Then we can compare to the integration along D and D prime prime. Then by the same argument, the difference along these two different passes is given by the residues of G of t along this. This is a so-called resurgence theory. Anyway, so in general, these two fundamental solutions are not equal to each other in their common domain. Yeah. Okay, now this is a so-called Stokes phenomenon. Now we can explain this Stokes phenomenon in more details and then answer Professor Krylov's question. Okay. Now the thing is that given these two properties in mind, what we can do is basically we can cut our complex problem by this Stokes race, and then in each of then we can take two offset. Then we can take two offset, for example, two offset sectors. Then we know that for each direction D, we get a solution. Then we can vary this blue race, and then to glue the solution together. In the end, we get a fundamental solution with the prescribed asymptotics in this region. And similarly, we can take the, because I don't have another color, but similarly, we can take the resummation along the direction in this region. Then we get a solution like in this region. I hope it's clear, but so basically we have one solution, let's call it F plus. So with the prescribed asymptotics in this blue region. And we get another solution, F minus, in the offset region. But both of them have the same asymptotics at z equal to 0. Okay, so this is a Stokes phenomenon. So recall that in the very beginning, I said that given a function, the Stokes phenomenon says that it can have different asymptotics in different sectoral regions. But now equivalently, I give you a prescribed asymptotics. Then this asymptotics, the form Paul series, corresponds to different actual functions in different sectoral regions. So this is another way to say the Stokes. Another thing is that since F plus F minus are the common solutions to a linear ODE, therefore their ratio is a constant matrix. And this constant matrix measure the jump or measure the non-uniqueness of the solutions. And this transition matrices are the so-called Stokes matrices. That is, I can give you the first definition, the so-called Stokes matrix. So the Stokes matrices are n-bind matrices, a pair of n-bind matrices of this system are the ratios of these two canonical solutions. That is, we can compare these two solutions in this common region. Then the ratio is a constant matrix that I call S plus. So this is in the region here. And similarly, I can introduce S minus. But the thing is that these two sectors, they don't actually intersect. You should take the continuation on the log plan. Then they intersect. So basically, the solution is always multi-valued. I may take exponential 2 by n and so on. But in any case, I can introduce two, invertible n by n invertible matrices to measure this jump phenomenon or the Stokes phenomenon of this linear system at the second order form. These are the so-called Stokes matrix. Okay, any questions? It is well, from the definition, it looks like a local theory, but one can use this local theory to solve some global analysis problem, like to solve the connection problems of the isomorphism deformation equations between different critical points and so on. Why is it? Because because S plus S minus are the complete invariants of this meromorphic OD. And from a more geometric term, so if we take a meromorphic connection on a disk or on P1 with a second order pole, so these are the monodromy data. Therefore, you can think of S plus S minus as the internal monodromy data of a meromorphic. Because that if you have a flat connection, the monodromy is when you go around some loops and so on. You should go around some loop. But somehow given a meromorphic connection, just at the irregular singularity, take a formal disk, you can find this monodromy. So it's an internal monodromy. All people call it irregular or wild character varieties. But in any case, we focus on this OD, and I hope this is clear. And this equation looks very simple, but somehow almost all the interesting analysis aspects of this equation is not known actually, like the WKB analysis and many other problems, the isomorphism deformation. And now so this is the introduction part, and now let me tell you how to relate this Stokes phenomenon to the Yang-Baxter equation. So recall that this Stokes phenomenon is you compare. So you start from one canonical solution with a prescribed asymptotics. Then you continue to some other sector. Compare these two solutions. It looks like the braid relation. Okay, so now let's construct for example, the quantum groups from this thing. So for that, I take some universal version of this guy. So I take UGON, the unitary associative algebra, and then I assume it has generators, the obvious generators EIJs, and then I take a matrix T. And then, well, for simplicity, let's take a finitely dimensional irreducible representation of UGUN. And then let's take a T. So this T is used in quantum integrability story. So so this is an n-by matrix whose ij entry is eij. Therefore, this is an element inside the endomorphism U lambda tensor with n-by matrices. So this is this is an n-by matrix, and each element is eij. And eij, given this representation, eij, the generators of UGN, can be seen as an element transformation on U lambda. So this is a way to understand this T. And similarly, I have a diagonal matrix U, which has, again, diagonal entries U1 to UN. But since this is a unitary algebra, therefore, each of these U1 to UN can be seen as a scalar multiplication on U lambda. Therefore, this U is also an element here. So this is exactly a universal version or non-commutative version of this system. That is, let's consider, now given this data, let's consider a more universal ODE. Let's put a Planck constant h bar and then plus T over Z times F. Now this meromorphic ODE has solutions valued inside endomorphism U lambda tensor by matrix. And now this dot, so this U plus T, this coefficient is valued inside this space. And this is just, this denotes the multiplication by n-by matrix and the composition by the linear transformation. Some highest weight. I label, the lambda is the highest weight, which label the irreducible. I take any, for example, finite dimensional irreducible representation. So lambda is just n numbers whose difference are integers, positive, non-negative integers, for example. Capital T is an n by n matrix, and each eij is element here. It's like in the RTT relations. The notation borrows from there. Okay, and now we can use. So this is a special case, of course. So this is, you can think of this as a block system with rank. So the rank of this system is now n times dimension of U lambda. But in any case, one can introduce a Stokes matrix, HU, HT. And they are now element inside endomorphism U lambda tensor by matrices. And then our first theorem says that actually S plus S minus give you the representation of quantum groups. That is, they satisfy the RLU relation. So for any non-zero, non-rational H and any for any fixed non-rational H and U, which is a regular element, which means U1 to UN, the eigenvalues are distinct. So this is a regular carton. The following map gives you a representation of UQGUN. So here the relation between Q and H is high I so UQ. So let's call it SU. It's mapped from UQGUN to endomorphism U lambda. that maps the Chevrolet generators EIFI to the off-diagonal elements of S plus, the ith row S plus one column element, and maps Fi to the off-diagonal element of S minus is a yeah. 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 So basically, this is a representation of UQGUN on the vector space U lambda. So recall that the Stokes matrix now are n by n matrix with entrance inside this endomorphism space. Therefore, each the off-diagonal elements are endomorphism, and it makes sense. So basically, this more or less this is. In other words, it says that S plus S minus satisfies the RL relation, RLL or RTT when you do the Gauss decomposition relation. And this explains the picture in the very beginning I drew. So the Stokes phenomenon, so the jump phenomenon of solutions near the irregular singularity corresponds to the Friday relation or the Young-Baxter relation on the group. Yeah. And this construction is universal. And actually, you can take the universal construction. And you can, here I take this differential equation. Actually, you can, there are many differential equations appearing in mathematical physics that have the irregular singularity, and one can study its Stokes phenomenon, and one can also construct like quantum symmetric pairs. So here I only take one example, but one can also construct like the quantum subgroup, quantum symmetric pair. Or Yangians, or even elliptic quantum groups by using the difference analog. Yes. So this is right. And here I want to give you a remark that if H is a rational number, the differential equation is resonant. And for a resonant differential equation, you don't have a unique formal solution. You have a family of formal solutions. And you have a family of Stokes matrices. And then for any fixed rational number, the Stokes matrix is also defined in quantum group representations, but at the root of unity. I guess I have 20 minutes. Rational numbers. Rational numbers. Rationals, yeah. Right. Yes. Not a small one. Small one you should take the quotient. Here I just if I have if H is not a rational number, then this is not a root of unity. Then this is, let's focus on this version. Not belong, sorry. If H is not rational, then the differential equation is non-resonant. Then it has a, okay. Well, if H is not a rational number, then this differential equation is non-resonant. that has only a unique formal solution. But if it's resonant, it has a family of solutions. Then it has a family of Stokes matrices. And recall that the representation of quantum group at the root of unity are not discrete. It's a family. And right. There are some cyclic representations. Right. Right. Ah, so this theorem says that the Stokes matrix give you a solution of Yang-Baxter equation, or equivalently, it gives you a representation of the quantum group here. Yeah. So if I take the Stokes matrix of this differential equation, then the Stokes matrices give you then I can construct a representation of UQG, which maps any Schauweiler generators like EI, Fi to the off-diagonal elements of Stokes matrices. Then this is a representation of the quantum group on the same vector space, U lambda. In other words, yes, yes, actually S plus S minus are the universal R matrix in UGON, not UQGON. Okay, okay. So since you ask, let's take the universal version, so which is maybe. Then let me in UGON. In UGON. So let me. Okay. So actually this says the following. So let's take the universal version. Then basically I can use the Stokes matrices of this guy to construct an algebra homomorphism from UQGON to UGON. So basically, so this is almost the isomorphism, but so this is a Drinfeld homomorphism from UQGON to UG. Yeah. That is a very good question. Yes. So to make it explicitly, I should solve Riemann-Hilbert problem, right? I should understand the monodromy of this system or that system. Yes. Uh, oh, 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 oh. So this this homomorphism is highly transcendental, right? So this is a highly transcendental map because the construction depends on solving the meromorphic ODE. So this is a transcendental map. So this is as I said, this is a soft part of the work. It's just a conceptual construction. There is no way to make it explicit. Yeah, it's a transcendental construction. And then, but somehow so this is a very soft part. But somehow it's, for me, the much more important thing is that given this conceptual construction, I can transfer many aspects of the representations of quantum groups into the Stokes phenomenon, and then try to understand, like the WKB analysis of meromorphic OD with higher rank, and then try to understand the Soliton solutions of meromorphic ODs, and then try to find the algebraic solutions of isomonodromy deformation equations. All of these questions are sort of open and equal. So for example, I give you, because I'm short of time, I just give you one hint. So On the left, we have the crystal limit. We have a crystal limit. That is, if I let Q goes to 0, then the quantum group will become some combinatorial state like the crystal or canonical basis. And if Q go to 0, then recall that if Q go to 0, then H go to infinity, plus or minus I infinity. This is exactly the WKB analysis for this differential equation. So this corresponds to the 1 over H go to 0, the so-called WKB approximation on the differential equation side. So that is a crystal basis or canonical basis under this construction should correspond to the WKB approximation of this linear ODE. For this particular one. Yeah, exactly. Yeah. Well, yeah. The thing is that if we take a Gromov-Witten or Furbius manifold, you consider its quantum differential equation given by the quantum product. The quantum differential equation is the isomonodromy equations of this linear system. And then I guess this WKB approximation corresponds to some genus expansions of the potential because this equation only encodes the genus 0 data. Okay. So there are two versions. I can either take a Q difference. That is, I discretize the differential. But here, what I take is more like a deformation quantization. So recall that this A has entrance Aij. They are commutative parameters. But now I replace by T with Eij or Heij. And this becomes non-commutative. But somehow if H go to 0, this non-commutative one, if you close under the filter, its filtered space is this. So in this sense, I take the quantization. So basically, if H go to 0, then we know that. So this becomes a symmetric algebra with the generators given by Aij. So in this sense, this is indeed a quantization. This is a quantization of the modular space of this meromorphic connection, which is a Poisson space by the Atiyah-Bolt construction. But I didn't say that. But yeah, I think it's time, and I stop here. Thank you for the attention.
Thank you for your talk. Yeah, but probably we still have some times for questions. And please use microphone to ask.
What happens in Pinrevec?
Yes. So
Stokes matrices is very interesting things for Pinrevec 6.
Yes.
For Pinrevec 6.
Yes. So yeah. So for if n equal to 3, so well actually if n equal to 3, the isomonodromy of this guy become Pauli 6. This was known. This was due to Hanat in '94, and then yeah. So for n equals to 3, the isomonodromy of this linear system becomes actually equivalent to Pauli 6. And then the boundary problem and the monodromy of Pauli 6 was solved in generic case by Jimbo. And in my plan, I was trying to talk about generic n to solve the Riemann-Hilbert problem for isomorphism. And then you can actually And as an application, you can find algebraic solutions for isomorphism deformation equations, which can be seen as a higher rank analog of Pauli 6. For n equal to 3, it becomes Pauli.
Okay, any other?
Yes. Difference. You mean Q difference equation? Okay. Yeah. It's a elliptic. Yeah. Yeah. So if we replace this by Q difference operator, then any formal solution, then if U is non-degenerate, then any formal solution is automatically holomorphic. There is no Stokes phenomenon. Yeah. But somehow if U is degenerate, for example, in our study, so if U is many zeros with 1, then it do have Q difference. Q difference. QZ or yeah, Q difference. Because then you get Q, then this becomes QKZ equation, which is related to elliptic. I think only when U is there is only connection matrix from 0 to infinity. If U is non-degenerate, if U want to UN if U is non-degenerate. Yeah, right. In some sense, something can be invertible in the formal set. Yes.
Okay, thank you for your talk again.
Thank you.
And now we have a lunch time, and please follow Andrei Tsiganov. He will show you where to have lunch.